Down.
Yep.
And we're recording.
Okay. Hi, Chem 30. I want to do a bunch of things today. The first thing I would like to do is look at. So what we're going to look at today is hydrocarbon derivatives. So we talked about extraction methods yesterday. I'm going to talk about some. So once we make finished products out of feedstock, we can modify them further for different types of industrial uses. So we'll talk about hydrocarbon derivatives. We're going to talk about some reactions that create hydrocarbon derivatives and what they're used for in petrochemical plants. So this is an important stat for us to know. In Alberta, 95% of refined crude and natural gas is burned as fuel. Now so most of this is used to make petroleum to fuel internal combustion engines, right? Only about 5% of our feedstock is used to produce petrochemicals, but this percentage is changing really quickly as we try to transition from being an oil and gas powerhouse to a jurisdiction that produces more and more petrochemicals. Okay? So raw materials, one thing we should understand, raw materials used as feedstock are considered a primary petrochemical. So, right, raw bitumen is a primary petrochemical. And very few of these primary petrochemicals have direct uses. They have to be further processed either by fractional distillation. That would be a secondary petrochemical, the products that come out of fractional distillation. So you get your octanes and your fuels, right? Your jet fuels, your kerosene, your bituminous asphalts and things like that. We can refine them further into tertiary petrochemicals where we modify them in industrial ways for different types of use. So this is a figure that's in your textbook. I'm just going to flip this over here in the textbook right here. Just move it down.
Oh yeah, I'm just putting it on the right. There you go.
Page 412. Okay.
Page 412.
So these are tertiary petrochemicals right here. And we have different types of uses for them. So ethylene and propylene will be used to make different types of plastics. And you can see modifications here. These are primary petrochemicals. And you can see the different uses these are different things that we make in Alberta. This is on page 413. This is figure 2. So you should take a look at that. Okay. These are all sorts of different types of petrochemical products that we use in industry or create an industry in Alberta. Okay. So I'm not going to spend a ton of time going over that, but it's something that you should review for the organic section of this unit. Okay? And that's what this is right here. So this is chapter 2, figure 2, chapter 10. So that was what I just showed you in your textbook. So it's also in your notes. And then this is something as well that would be useful to look at. This is also in your textbook, and it's on page 414 and 415. Okay, so this shows the different types of jobs created from different types of petrochemicals. So starting with ethylene, so plastic, all the different types of uses we have for it. And then these are the different petrochemical companies that use this feedstock and where they're located in Alberta. And you can see Interpipeline is in Cochrane. So these are all these different types of petrochemicals that we use to make tertiary petrochemical feedstock that we use to make tertiary petrochemicals, and we use them for all sorts of different things. So I'm going to talk about a bunch of different types of uses, and we produce a lot of them in Alberta. So that is page 414 and 415 in your textbook. Okay? Okay, so the first type of hydrocarbon derivative that we're going to discuss is organic halides. Okay, so organic compounds are divided into hydrocarbons and hydrocarbon derivatives. You already know this. The hydrocarbon derivatives contain carbon, hydrogen, and at least one other element. So the derivatives are halides, alcohols, carboxylic acids, and esters. And we can take all four of these and turn them into polymers. So those are the main derivatives that we're going to focus on in Chem 30. So these are end product modifications. Now some alcohols and carboxylic acids and esters, they exist naturally in the environment. These don't. Okay, so there's no naturally occurring organic halides or halogenated hydrocarbons, but we produce most of these for our own uses as well, right? So hydrocarbons are non-polar, but hydrocarbon derivatives, because they have fluorine or chlorine or oxygen, they end up being polar. So that completely changes their properties, right? Okay, so organic halides, they have one or more hydrogen atoms replaced by atoms of chlorine, fluorine, bromine, and iodine. So organic halides are anything that has a hydrocarbon chain with group 17 elements attached to them. So those are halogens, right? So the functional group is the halogen. So one thing we should see with these derivatives is we should understand what a functional group is. So a functional group is the unique part of a hydrocarbon that determines the most important physical and chemical properties. Okay? So let's start with this guy. This is obviously one carbon. So this is a methane group. Now, so this is methane. Can you see that green marker?
Not well. Just so you know too, I've been having fun with this filming stuff. Just
Glad
say.
I'm here to entertain you.
Well, of course.
Glad I can entertain you. So methane. So what we have, so we have a methane group, and then we have one bromine molecule attached to it. So the main ones that you're going to see are bromine. So when we look at halogenated hydrocarbons, bromine, chlorine, fluorine, and iodine. Those are the main halogenated hydrocarbons you're going to see. Now what we do to name them is we drop the I and E and add OMO, or MO, or O, all right? So this ends up being bromo, methane, okay? If I had a chlorine, it would be chloromethane, or fluoromethane, or iodomethane. So you drop the I and E and add O. And I'm going to go through a bunch of examples. So the general formula is, for organic halides, is Rx, where R is the hydrocarbon chain, and X here is a halogen. So there's a halogen attached to an R group, and the R group is the hydrocarbon chain. Okay? So, rules for naming halogenated hydrocarbons: you name the parent chain, find out halogen atoms in the molecule and circle them, determine the appropriate prefixes to represent the halogens, and communicate where each halogen atom appears in the parent chain. There's examples on page, I'm going to erase all these acid-base examples, because these are in my notes, and we're pretty much done with that anyway. So page 418, numbers 1 through 5 addresses halogenated hydrocarbons. So let me give you some examples here. So let's say we have so these rules, they're very similar to alkanes, alkenes, and alkynes. These are a few examples of halogenated hydrocarbons. Okay, CFCs are chlorofluorocarbons. So let's start here with the naming. Freon 11 and Freon 12. This is the common name for them. These are refrigerants. Okay, so they're synthetic organic molecules where hydrogens are replaced with chlorine and fluorine. They're used as refrigeration and air conditioning molecules. So if I look at what the name of this is. So Freon 11, let's draw it. Okay, the common name is Freon 11, but it's actually a methane molecule. Right, there's one carbon, and all the hydrogens have been removed. So the way I name this is, so I have, on one carbon I have 3 chlorines, and I name in alphabetical order as well. So this is trichloro, fluoro, methane. Okay? Now they're all on carbon 1, so I don't need to answer. It's understood that they're all on carbon 1, so I don't need to put like 1, 1, 1 trichloro or anything like that. But the naming rules are the same as side branches, all right? So the prefixes that distinguish how many of them are don't count in alphabetical order. That's why I put the chloro first. Halogenated hydrocarbons are also named before methyl, ethyl, and propyl groups, as well as phenyl groups, right? So halogenated hydrocarbons come before side branches when we name, because we'll have some molecules that have both. So just be aware of that, okay? So Freon 11 here would be trichlorofluoromethane. Now if I look at Freon 12, this is, again, the parent molecule is methane. And this ends up being dichloro, because there's 2 chlorines, and difluoromethane. Difluoromethane. All right? So we'll talk about the consequences of this, but remember that these molecules are very polar, right? The fluorine and the chlorine. So fluorine has the capability to make hydrogen bonds. Okay, so this totally changes the dynamics of how hydrocarbons work. So I'll come back to that idea after I do some examples. Okay, so let's take a look at a few of these. So if I look at the parent molecule here, this is 1, 2, 3, 4, 5 carbons. So this is pentane. And then nearest side branch, which the halogenated hydrocarbon is your nearest side branch, is at this carbon. So this is carbon number 1. Okay, so that's a methyl group right here, and these are halogenated hydrocarbons. So the way I name this is I have 1 chlorine, so it's 3 chloro, and then I have 1 fluorine, and it's 2 fluoro. And I have a methyl group on carbon 3, and that ends up being 3 methyl pentane. Okay? Now the next question I can ask you is this polar or not? All right. So if I look at the dipoles with these guys, we know that chlorine and fluorine are electronegative. So, and then this is nonpolar. So overall, the molecule has a dipole that points in this direction. So this molecule is polar. Okay? So that's something that you should be able to pick out with any halogenated hydrocarbons. Is it polar or not? Let's look at this one. Okay, so again, this is similar to the Freon molecules. This is trichloromethane. And is it polar? So I've got a dipole that points this way, a dipole that points this way. So those cancel out, but one that points this way. So it is polar because this one doesn't cancel the chlorine out. All right? So the trichloromethane is polar. This is chloroform. the common name, by the way, right? So that is, this is an ether. So an anesthetic, okay? So if you've seen like James Bond movies or whatever, and they knock people out with a napkin, they're using chloroform to knock the person out. All right, what about this one? So let's draw this one. 1,3-dichlorobenzene. Okay, so what does this look like? First and foremost, it's a benzene molecule. Okay, so there's your benzene molecule. And I'm going to have a chlorine on carbon 1, and then it's spaced one apart. So there's a chlorine here. Now I could put them anywhere. They just need to be spaced apart. Okay, now if you remember, this would be, if I could do this too, right? Chlorine here, and I can also have chlorine here. Right? And this is, that would be O, that'd be ortho dichlorobenzene. This one would be para dichlorobenzene, and that would be meta dichlorobenzene, right? So you have the Greek prefixes based on what the chlorines are, because these are all identical molecules with slightly different configurations. So the same rules apply for that, okay? Oops. Let's look at this one. CF2, CCl2. So there's two carbons, and then there's two fluorines attached to this, right? CF2, CCl2. Okay. It's understood that the other molecules are hydrogen. Okay, now remember that halogens they bond the same way hydrogen does because they only need one valence electron to be stable. Right? So this is a very condensed chemical formula. Alright, so it didn't include the hydrogens. So, what is this? This is an ethane molecule. Okay, and I'm going to number this carbon 1 and this carbon 2 because the chlorines are here. So this is 1,1-dichloro, and then 2,2-difluoroethane. Okay? And now would this be polar? I have a dipole here and a dipole here, a dipole here and a dipole here. So these would cancel out. And that would be nonpolar. Okay? So let's talk a little bit about these chlorofluorocarbons, just so you know what we use them for and some of the effects of this in the environment. So so if we're talking about good news stories about the environment, the ozone layer is actually one that humans haven't totally, we messed it up and then we figured it out. So chlorofluorocarbons, they're in aerosol cans and they're in refrigerants and things like that to maintain pressure. They're very, very stable. Right? So again, there's nothing in the natural world that has hydrocarbons with halogens attached to them. Therefore, there's nothing in the natural world that decomposes them. So, as I said yesterday, these end up being persistent organic pollutants. And most of these guys could also be polycyclic aromatic hydrocarbons. Okay? So, if we look at where the ozone layer is, okay, high above Earth at the top of the stratosphere. You're right above the troposphere where the weather is. At the top of the stratosphere is where our ozone layer is. Now, ozone layer is O3. Okay, so the top of the stratosphere is kind of where planes fly, when planes are flying. All right? So ozone, what we use O3 for is it's necessary for deflecting ultraviolet radiation. Now, this is not the greenhouse effect, right? The ozone layer, what it does is it deflects UVA, well, mostly UVB and UVC, ultraviolet radiation, and that helps us from being bombarded with ionizing radiation that causes mutation. Okay? So, the ozone layer can lead, right, if it didn't work, it would bombard us with all these ultraviolet radiation, and that could lead to mutated DNA and skin cancers. So here's what happened with the ozone layer as we started to use these aerosols. Because of the polarity of the F and the Cls in the chlorofluorocarbons, as we started using CFCs, they ended up in the atmosphere and they diffused up to the ozone layer. Now, these chlorine and fluorine molecules, because of their polarity, what they did was they broke up the oxygen. And remember, oxygen itself is also quite polar, right? It has your bonding electrons that are free. Okay, so as a result, the chlorine and the fluorine interacted with the oxygen and broke up that ozone. So this is how free radicals work in your body, by the way. And in fact, a lot of free radicals that mess your DNA up come from oxidation reactions, and it's because of that polarity that they interact with your DNA and break your DNA up. So this is the same free radical action that happens in your body. Okay? So the CFCs break up the ozone and they cause a deterioration in the size of the ozone layer. So we had big holes in the ozone layer at the turn of the last century. Now we've been able to deal with this because we've taken CFCs out of the atmosphere. We don't use them anymore, so the ozone layer has come back. So this is actually kind of a good news story. So if we can solve the ozone layer, there might be hope for humans to solve things like climate change, because it was a big international agreement to ban CFCs that the international community had to coordinate on. So CFCs are responsible, right? So these free radical chlorine atoms, so these ionized chlorine atoms, right? They attack the ozone molecules and they break up the ozone layer. Okay? So when they interact with sunlight, they did that. So these CFCs, even though they're really useful because they're stable, have had unintended consequences. So here's some other examples. All right, this is ethylene, and again, the ethylene is the basis of plastic. Okay, so this ethylene, we can remove some of the hydrogen molecules, and this is still an ethene molecule, and we've turned it into tetrachloroethene. So 4 chlorine atoms. Okay, this is a very common molecule in hard plastics. Ethane here, you can see we can remove some of the hydrogen atoms and add bromine. This would be 1,2-dibromoethane. So some other examples of common halogenated hydrocarbons. DDT, right? Pesticide. Right? It was that it spurred books like Silent Spring, which brought about the modern environmental movement. DDT is no longer used in Western nations as a pesticide and a herbicide because these hydrocarbons are fat soluble. So what they did was they dissolved in the lipid tissue of organisms, and then it bioaccumulated up the food chain. So this DDT got transferred, and so if you remember from maybe learning this in elementary school, what the DDT did was with birds of prey, it greatly thinned the eggs of apex bird predators. So raptor species like peregrine falcons and hawks and bald eagles and things like that. So this DDT thinned the eggs as it bioaccumulated in the fat tissues of these apex predators. And as a result, a lot of these animals almost went extinct. So we banned the use of DDT, and a lot of these animals have made a comeback. Toxaphene, polychlorobiphenyls, so PCBs. These are used in plastics like water bottles. Dioxin is Agent Orange, right? So if you remember anything about the Vietnam War, right? Dioxin was used to defoliate the rainforest, and then they could, and then the U.S. and their allies could see the Viet Cong, and this dioxin bioaccumulated in natural environments, and people in villages in Vietnam are still feeling the consequences of that. So there's been genetic mutation, and families are affected with weird types of endocrine cancers and spinal cancers, and babies are born without limbs and genetic mutation and things like that. So, so dioxin it was used as Agent Orange, but it's also used as used in tanning facilities. So tanning meaning like tanning of leather, not like, you know, like put it all over your body to make you give you a fake and bake, right? So furans are also used for that as well. So furans are used for artificial tanning of leather. So in developing nations where a lot of our clothes are made, they use these types of chemicals in order to make their jeans, and then if they don't have a proper way to dispose of these chemicals, they end up in the water supply, right? So places like Bangladesh and the Philippines and in other places in China or Vietnam, now that have basically become the sweatshops of the world, a lot of these end up in the water supply because there's inadequate ways to treat these volatile chemicals. So here's the deal, is halogenated hydrocarbons are very stable and they last an extremely long time. So it's good for their industrial purposes, but it's not good when they get into natural ecosystems. So like I said, human activities are the only activities that create halogenated hydrocarbons, and they could cause damage in the nervous system, kidneys, liver, and heart. So we need to be careful with how we use them.
Okay, let's pause there because I got to go to class.